In this video, I'd like to talk about the math question of the day for March 26th, 2023. And with this problem, we need to identify the equation of the line tangent to the point at x equals 0 for the function below, where our function is 4 multiplied by the arctan of 2x. Or, in other words, this is 4 multiplied by the inverse tangent of 2x. So to answer a question like this, to find the line tangent, we will need to take the derivative of this function because the derivative will tell us the rate of change, the slope of the line that's tangent to some specific point, some specific x value. And from there, we can figure out the equation of the line. So we need to take the derivative of this function. So you need to understand calculus, or specifically differential calculus, but you will also need to understand a fair amount of trigonometry to make sense of everything. So at this point, go ahead and pause the video, see if you can work through this on your own, and when you're ready, we can go through this together. Now, assuming that you have attempted the problem, let's start working through this. And if you do have suggestions for future videos, feel free to leave those as comments. Now, I will start by just rewriting this function, and I will use the inverse tangent notation, but the arctangent notation means the exact same thing. So either way you want to write this is completely valid. Now, notice that we have a function within a function. We have a composite function here. This function 2x is within the outer function, which is the arctangent function, or the inverse tangent function. So when we take the derivative of this, we will need to use the chain rule, which deals with composite functions, or the derivatives of composite functions. And we will also need to know how to find the derivative of the inverse tangent, which can be a bit challenging. So this question is fairly difficult, but it can be solved from basic principles. So let's start with the scenario. Let's say we have g of h of x. We have some random composite function, and we want to take its derivative. To do that, we take the derivative of the outer function, this function g, and we leave the inner function as it is, and then we multiply by the derivative of the inner function. So this right here, this is what we call the chain rule, the derivative for composite functions. And then we will also need to find the derivative of the inverse tangent function. So let's consider that before looking at this more complicated function. Let's say that we have y is equal to the inverse tangent of x, and we want to find the derivative of this function. Now, personally, I don't memorize what the derivative of the inverse tangent or of the inverse trigonometric functions are. I like to derive them from scratch whenever I use those, just so that I don't have to memorize a lot of knowledge. I can always pull that knowledge out from basic principles. So let's start by taking the derivative of this function. And to do that, it will be best to rewrite this without this inverse tangent part. If we can just get the tangent back, this will be a lot easier. And to do that, we can take a tangent of each side. Or in other words, we can put each side of this equation inside the tangent function. So the tangent of y is equal to the tangent of the inverse tangent of x. But notice on this side that we're plugging the inverse inside the function. And whenever that happens, they essentially cancel each other out. You might remember the general property. Let's say we have k of x. When we plug k of x inside its inverse function, they cancel each other out and we just get x, though it also works the other way. If we plug the inverse function inside the function, we still get back x. So we apply that principle here, we get the tangent of y, this is just equal to x. And from here we can find the derivative of this function with respect to x. So let's actually just clear this off and start from scratch. We have the tangent of y is equal to x, but we want to find the derivative of this with respect to x, since x is our independent variable. So we will need to use implicit differentiation. We find the derivative of the outer function here. We're using the chain rule. And the derivative of the tangent is the secant squared. We will just rewrite that inner function. And then we multiply by the derivative of the inside. But the derivative of y with respect to x, we can just write as dy dx or as y prime, whichever way you want to write it. This is ultimately what we're trying to find. And the derivative of x with respect to x, that's just 1. We can use the power rule for that. You bring down the 1 and then subtract 1 from the exponent. You get 1 times by x to the 0, and anything to the 0 is just 1. So the derivative of x is simply 1. And like I mentioned, we just want to solve for the derivative of y with respect to x, since that is ultimately what we wanted to find. We started with y is the inverse tangent of x, and we want to figure out what the derivative of this function is with respect to x. That's our goal here. So we divide each side of the equation by the secant squared of y. We get dy over dx is 1 over the secant squared of y. And we just need to figure out what this is in terms of x. But remember, with trig functions, you can draw triangles. From this equation here, this tangent of y is equal to x, we can draw a right triangle and use the properties of trigonometry. It looks like because y is the input of the tangent, that's our angle. Whatever the input of the trig functions are, not the inverse, but the regular trig functions, that's the angle we're dealing with. So our angle is y. And we know that when dealing with SOHCAHTOA, the definitions for right triangle trigonometry, that the tangent is the opposite side divided by the adjacent side. If we set this up as a ratio, x would be the opposite side and 1 would be the adjacent side. So opposite the angle, we have x, and adjacent to the angle, we have 1. And if we want, we can figure out the hypotenuse. That can be found using the Pythagorean theorem. It's just the square root of 1 plus x squared. Since if we gave this some letter, let's say h, we have h squared is 1 squared plus x squared, and we just square root both sides of this equation. And from this right triangle, we can figure out what the secant squared of y is. Since remember that the secant of y is just 1 divided by the cosine of y. Since secant and cosine are related, they are reciprocals of each other. And we know that the cosine is adjacent over hypotenuse, so the secant is the reciprocal of that. It's the hypotenuse divided by the adjacent side. It's the ratio of those two sides. And we can just look at our triangle now. The hypotenuse is this square root of 1 plus x squared, and the adjacent side is 1. So the secant of y is just the square root of 1 plus x squared. But when we actually square it, like we have here, the square root and the square will cancel, and this just becomes 1 over 1 plus x squared. So all of this work to derive the fact that the derivative of the inverse tangent function is 1 over 1 plus x squared. And from here, we can use this information to take the derivative of our function. Though, like I mentioned, we will also need to use this chain rule since our inside is a function of its own. It is the function 2x. So let's make a little bit more room over here. We can keep working. And now we can take the derivative of f of x. We want f prime of x. We take the derivative of the outside first, and this 4 will just carry along. But remember that the derivative of this outer function, this inverse tangent, is just 1 over 1 plus x squared, or 1 plus whatever the input is, squared. So that 4 will just distribute to the 1 in the numerator, and then we have 1 plus x squared if we're dealing with the inverse tangent of x, but since we're dealing with the inverse tangent of 2x, we would have 2x, and we're squaring that. And then we multiply everything by the derivative of the inner function, and the derivative of 2x, that's just 2. since again we can use that power rule, bring down the 1, we multiply, then subtract the exponent, we get x to the 0, which is 1, and 1 times 2 out front is 2, so 2 times 1 is 2. Now simplifying, we'd have 8 over 1 plus 4x squared, since we're doing 2x times 2x, which is 4x to the second power. Now, keeping in mind that this derivative of our function, this is just the rate of change of our function, and I won't actually draw this function. And let's say we have some other function, which we can call m of x. When we find the derivative of a function, it just tells us, when looking at a specific point, what the steepness of the curve is at that point, or it tells us if we draw a line that's tangent to the function at that point, the derivative will tell us what the slope of this line actually is. And we need the equation of the line tangent to the point at x equals 0 for this function. So we need to find the derivative when x is equal to 0. We can plug that in. We want f prime of 0. We get 8 up top and 1 plus 4 times 0. So we just have 1. So the derivative at an x value of 0 is just 8, which means that if we had a picture of this curve and we drew the tangent line at this point, that slope of the line would just be 8. It would have a steepness of 8. Every time the x value goes over 1, the y value will go up 8 around that point. And we need the equation of the line. We don't just need the slope. So let's look at the equation of a line using our slope-intercept form. We have y equals mx plus b. We know what m is. That's 8. So we can rewrite this as y equals 8x plus b. But we need to find what b is equal to. And to do that, we can look at the x and the y value at that specific point. We know the x value is 0, but we don't know the function value at that point. We need to plug that in. So we need to find what f of 0 is. Let me just make a bit more room so we can keep working on this. We are running out of space here. But let's say we have f of 0 now. We're just plugging 0 into our function. We get 4 multiplied by the inverse tangent of 0. And the inverse tangent of 0 is just 0. So this function at an x value of 0 has a y value of 0 as well, meaning it just goes through the origin. And if we plug in x and y both equaling 0 here, we can find b, but by doing so we would get 0 is 0 plus b, or b is 0. So the equation of the line that is tangent to this function at an x value of 0 is simply y is equal to 8x. So this right here will be our final answer.